Okay, part two of 7-1 graphing exponentials, and we're going to scroll all the way down here and do the applications. And I'm going to back up and, oh wait, I already filled that in. Okay, fine, we'll start from here. Hopefully you can see that after year one, you start with $1,000, you're in 4% interest, 1,000 plus 0.04 times 1,000 equals 1040. And I'll tell you what, why don't you hit pause on the video and on your own worksheet, actually go through and do years 2, 3, 4, and figure out how much money you have at the end of year 4. Okay, hit pause. Okay, I'm going to come back now, and hopefully you've already calculated this, and you were clever enough to say, hey, hold on, I could actually done that in a single step, and that's the same as doing 1,000 times 1.04. And notice that'll get you straight to 1040 without having to actually do the whole addition part. So notice on the next year, I would start with 1040. And then if I had 1040 times my 1.04, then that would get me to what? 1081.6. Now, okay, fine. I'll just keep going here, and I'll note I'm doing different years and different colors for a reason. I would start the next year at 1081.6, and then I would have 1081.6 times 1.04 is equal to what? 1124.86? Not 1124. 86. Now, the part gets clever here when you're saying, hold on a sec, 1040. That was the same as my original 1,000 times 1.04. And this 1081.4 here, let me rewrite all of that, John. 1081.4 is the same as all of this stuff. And I'll just write it like it was originally, 1,000 times 1.04, which got me 1040. I multiply that by another 1.04. That got me to 1081.4. Then if I multiply that by yet another 1.04, 1,000 times 1.04 times 1.04 times 1.04 is the 1124.86. And lo and behold, now I have a simple way to do this for, try to do year 25. Go ahead, hit pause. See if you now know the simple formula for compounded interest. If you can figure it out and do year 25. Hit pause, go. Okay, we'll come back. Hopefully you actually did this. I haven't done it. I just made the problem up, so I'm going to work it right now. I'm actually not pausing. So what we're seeing for year 4 was, I should have been able to do 1,000 times 1.04 to the 4th power, which, I don't know, I think I can type right in here. Let me space this out here. 1,000 times 1.04 raised to the 4th equals 1069. Okay, fine. Right here for year 20, well, it's getting out of line, isn't it? I'll type, that way it doesn't mess things up. Don't forget you can type on these forms and they'll do the calculator math for you. 1,000 times 1.04, no, I can type 1.04 to the 25th equals 2,206. And you know, it didn't triple, but somewhere between doubled and tripled my money, and that's only with 4% interest rate, and therefore this is why I start saving early for retirement, because it can grow pretty darn fast. And that's the basis for our compounded interest formula, which is A equals P 1 plus R over N to the NT. Now P stands for, I'll call it principal. Let me make this bigger so I can write a little bit neater. Principal rate, specifically R is my annual rate. That's the way these things are set up. T is the time in years. N is the number of compounds per year. And you will only see this with banks. We're going to do exponential growth and decay and things with house values or car values, etc. This only works, this compounding idea with the n's inserted in here only works when you have banks. So for example, if it's compounded monthly, that's the easiest one to understand, then n equals 12, and what that does is it converts to a monthly rate, my annual rate, into a monthly rate, and then the same thing converts to from a number of years into a number of months. Okay, easy enough. Let's try to use a formula. Go ahead and plug these numbers into this formula and see if you can get an answer. Hit pause, do it. Try it just like we would in class. Okay, I'm back. Hopefully you did it already. I haven't yet. But I think I can just type this out. It's pretty easy. 5,000 bucks into the bank. 1 plus 0.035. Don't forget to move your decimal place because you have to from percent down into decimals. What is this? Compounded monthly. So we're going to divide this by 12. Then I have a monthly interest rate. Now when I raise that to a number of months, I think I better put a parenthesis around the 12 years times 12 months per year. So basically I'm going to add interest 144 times. And if I add equals, hopefully that's right. Hopefully all the PEMDAS within the OneNote worked out. And I get 7,605. And let me change this color. There, that's better. It doesn't look like the text then. Okay, let's go on and do B. 1960-90 population of Texas. Notice there is no compounding here. This is not a bank that can choose to just add interest into the account at the end of the month. It's an annual growth rate. Gives the population in terms of years since 1960. Fine. This would be simply it's still the principal is my beginning population, which is 9.58 in this case, and I'm still have a interest rate or a growth rate of 1.94%. So it's simply population in year 30 will be equal to 9.58 million. 1 plus 0.0194 raised to the 30th in this case, right? 30 years after 1960. Yeah, what is that? I don't know. Let me try typing it. 9.58 times 1.0194 raised to the 30th. Okay, 17 million. I don't know how accurate that is. Same deal. I think we'll do one more and then we'll call it a day. I think you're getting the idea. Hopefully this is a good enough review from the stuff you did last year in Algebra 1 class. And you buy that BMW. Now, luxury cars are having a lot of impact from Tesla. There's the Tesla effect causing luxury car depreciation has always been high. They're a terrible investment, especially considering insurance cost. But even more so now because Teslas are causing BMW and Mercedes prices to drop even faster. Depreciates 9% a year. What's my inflation, my interest is not going to add to the value, it's going to take away from it. So in this case, my principal, the value, I don't know what do we use? A, the amount it's worth, the value, we'll just call it A. My principal in this case is the $55,000 a year. I'll just put it in, I'll write the whole 55,000 out so it doesn't confuse anybody. Depreciation is not positive, it's negative. So it's 1 minus 9%. It was 9%, right? 0.09. And that's a point in time. Now, if it's 10 years, that'll be the 10 at the top. Yeah. Now, here's what I want you to notice. 1 minus 0.09 is 0.91. That means at the end of the year, each year, it's worth 91% of beginning of the year. I'll just write begin. So at the end of year one, it's worth 91% of when you bought it. At the end of year two, it's 91% of the 91% of what you bought it. So if I type this in, 55,000, no, that times, I'll just do the 0.91, keep it simple. I don't need parentheses then. 0.91 raised to the, what, 10 years? 21,000. And that actually might be high for a 10-year-old car, so maybe depreciation is more like 12% a year. And you can see I lost most of my value in the car over those 10 years. Okay, hopefully this is good enough on exponentials and exponential growth as a reminder of things. Ciao.